All right, so we're very happy to have David Hidrose from UNC, who is going to talk to us about webs in Type C.
Great. Yeah, thanks for the introduction. Thanks for the invitation. It's great to virtually be in Oregon, although not quite as nice as being actually in Eugene in the summer. But nevertheless, still here to talk to you a little bit about, well, I guess the title was maybe Webs in Type C, but then after I started writing the talk, I realized that I spend most of the talk basically just talking about webs in general, because the Type C stuff is the more recent stuff, and the answer will be, well, here's a definition and here's some theorems about it, which hopefully will have context provided with maybe the first bit of this talk. Great. So I should maybe mention at the outset that most of this stuff, or at least most of the new stuff here, is joint work with Logan Tatum, who I guess until 8 days ago was a grad student at UNC, now on to bigger and fancier things. And time permitting, we might also touch on some work in progress with Bodish, Elias, and Tatum. Okay, so maybe first some generalities. So here's a very general problem you can state is, well, can you find a generators and relations presentation of an interesting monoidal category? I mean, you can say this problem more generally even as find a generators and relations presentation of something you find interesting, but this will be this particular version of the problem considered today. And so maybe the first thing to think about is what should such a presentation look like? So I guess I haven't defined a monoidal category. Probably most people attending this conference at least are familiar with categories. And a monoidal one is one that has a nice notion of tensor product. So one thing to recall is that, I guess maybe dating back to some physics literature, we can depict morphisms in monoidal categories diagrammatically. So here, if I have some morphism from some tensor product of objects to some other tensor product of objects, what I do is I somehow list those objects, the bottom and top. I'll read everything bottom to top. And then I describe this morphism via this coupon in the middle with strings coming off of it. And you should think of those strings as essentially being labeled by those objects. So here I see strings labeled x1 through xm at the bottom, y1 through yn at the top. And this coupon will just be just some good notation, I claim, for a morphism in a monoidal category. Why is this good notation? Well, of course, when you're talking about settings where you have a notion of tensor product, you can take tensor products of things. And so diagrammatically, if I want to take the tensor product of two morphisms, I just place their pictures side by side. And what you'll notice is then when you do that, you place all of the labels at the bottom and top also side by side, which is of course just diagrammatically how you would, or maybe not even diagrammatically, traditionally how you would denote the tensor product of things which are themselves tensor products of things. Maybe for the uninitiated, I should also just mention that if you want to compose, this also can be described diagrammatically just by putting one thing on top of the other. So this diagrammatic language really is useful in sort of capturing the operations possible on morphisms in a monoidal category. Okay, so that's just a bit of maybe the classical facts about monoidal categories. So given that, what do we expect? Well, if I want to present such a category, I'm looking for some set of generating diagrams. So much like if you're presenting, say, a group or an algebra, you would ask for some generating elements of that group or algebra. And then I'd expect some relations between these diagrams. And maybe expect here is a strong word. So maybe one thing that you might hope is that the relations you end up writing down end up being local in some sense. You need to write some relations which are maybe local to these pictures, and then, well, if you're in some nice enough setting, you might hope that some collection of local relations then propagates and tells you all of the relations between morphisms in your category. Okay. So I had this word interesting up here. So today, what my definition of interesting is will be categories of quantum group representations. Specifically, I want to think about finite dimensional representations, and maybe I should even say type 1 finite dimensional representations for those who know what that means. So finite dimensional representations of quantum groups, and quantum groups, again, today associated to simple complex Lie algebras. If you don't have a background in quantum groups, you could instead just everywhere you see a Q, plug in the number 1, and think that I'm looking at finite dimensional representations just of a finite dimensional simple complex Lie algebra. Okay. That's maybe the bait. Now here's actually a switch. What we'll actually be interested in is a certain full subcategory that I'll denote by FREP. And this is the full subcategory, well, generated in a monoidal sense. So again, another story today is all about monoidal categories. And so I want to look at the full subcategory, tensor generated by the fundamental representations. And again, if you don't know quantum group representation theory, hopefully you know some statements about, say, the representation theory of simple complex Lie algebras. So you know what that means. Maybe the important takeaway, if you don't know what a fundamental representation is that in some sense the category tensor generated by the fundamentals contains all of the information about sort of the complete category of representations. And this can be made precise via this operation of Karoubi or idempotent completion. So the idea is we have a category that maybe we're really interested in, and we find some somewhat more manageable replacement from the perspective of generators and relations, from which we can recover the thing we're actually interested in a at least conceptually straightforward way, although practically it's a bit more involved. Okay, so why do we care about such things? Well, in the case of these specific monoidal categories, there ends up being extra structure which allows me to essentially define invariants of knots and links from these categories. Specifically, these categories of quantum group representations are not just monoidal, but they are braided monoidal, which means that if you see a little piece of a knot that looks like a crossing, then you can assign to that some morphism in the monoidal category. And further, these categories end up having a ribbon structure, which ends up effectively just translating to the fact that you get invariants of I should say framed knots or links. Okay, so one reason why we care about such descriptions is these categories give us link invariants, therefore maybe explicit descriptions of these categories give us tools to study these link invariants. Maybe a related reason to care about giving presentations of these monoidal categories is that they, in some sense, form the foundation for link homologies. And I'll comment a bit more on that in a second. And the final thing, which I think maybe Daniel's talk yesterday, if I was reading his slides correctly, maybe set the stage for, is understanding that diagrammatic presentations of these monoidal categories maybe is the first step towards understanding some more sophisticated monoidal categories that were appearing in his talk. So structural properties, applications, and representation theory, let's say. Okay. Questions before we move on? All right. So I want to start just by maybe observing what's known about this problem. And the way that we'll go through this is we'll just start listing complex simple Lie algebras, and we'll start with the simplest one and work our way up to more complicated ones. So of course, the first place to start is just with SL2. And in this case, there's a long history to this problem. Maybe this is a folk theorem in like the best sense, that there's sort of a long storied tradition of these results that keep getting maybe rediscovered and refined. And so maybe the earliest place that I've seen this sort of stuff referenced is in this old 1932 paper of Romer, Teller, and Weil. There are actually even pictures in that paper. So there's diagrammatics right in the first maybe appearance of these sort of considerations. And then certainly some of this stuff was discovered in some form by Temperley Lieb. And maybe just to fill in the ... a bit, this then later appeared in work of Kaufman and Jones in some form, revisited by Cooperberg, and we'll see more of that in a second. And maybe some other names that I should mention, because this really helped to make this very precise, is work of Snyder, Tingley, and Tingley. Peter Tingley has a great paper where the title is something like "A minus sign that used to annoy me." Is really a great read to sort out this SL2 stuff in detail, and actually highlights an important issue, which maybe I'll touch on. All right. Without further ado, let me stop naming names and move on to the actual theorem. Here's the statement. So you look at this category of fundamental SL, tensor generated by fundamental SL2 representations. Of course, there's just one of them. It's just the standard representation. And the theorem is that that's equivalent to, and I'll say it maybe in fancy speak first, and then we'll elaborate. It's a CH1Q linear pivotal category freely generated by a single self-dual object modulo one local relation, which is this circle relation. It's depicted right here. Maybe I should remark that quantum 2 is just Q plus Q inverse. And we'll see further analogs of that as we move on. Okay, so that's kind of a mouthful. Let me translate. Translating this, well, if I have a single object as my generating object, what can I do? I can take lots of tensor products of that object with itself. And so I can index objects in this category just by giving you a natural number. It's how many copies of this generating object I've taken the tensor product of. For me, 0 is a natural number because I want to be able to take no tensor products of the thing with itself, which gives me the monodal unit as an object. And then I have this word pivotal somewhere in here. Well, as soon as I have that object, well, first I need its identity morphism. So that's just this upward line. That's the identity from my generating object to itself. Some of the things involving, the monodal unit are just sort of empty things. But pivotal tells me that I have some dualities floating about. I said self-dual, so this object is dual to itself. And so what I should have is I should have maps that realize that duality. So these are these cap and cut maps that take me from object tensor itself to sort of the empty tensor product of the object with itself. That's this one right here. And one that goes the other way, a morphism which goes from the monodal unit, the sort of empty tensor product, to my generating object tensor itself. So somehow hidden in these words, self-dual and pivotal, as the fact that I want these cap and cup morphisms. And you always want identity morphisms, which will just be depicted by the line. And so also secretly hidden in this definition, secretly hidden in the word pivotal, are some implied relations. And that's this relation of planar isotopy, which essentially says that if you draw some picture built out of these pieces. And remember, I'm allowed to build things by placing pictures side by side or gluing top to bottom. It turns out that if you do that, you can build, say, any planar curve with some prescribed top and bottom boundary points. Well, I want to allow these curves to be viewed as the same if I can wiggle one to another. So that's implied by this word pivotal. And the topologist would say that what I'm allowing is planar isotopy relative to the boundary. And then, of course, I'm on up by this circle relation. Okay. So that's the theorem. Interestingly, it provides kind of a bridge between representation theory and low-dimensional topology. We described some representation theoretic category in terms of somehow some of the simplest low-dimensional topological objects, just curves embedded in the plane with prescribed top and bottom boundary. Okay. Further, this category I claim is ribbon. Which is some combination of the word pivotal up here, having a braiding, and then some nice conditions that braiding satisfies. And so here I've depicted what the braiding is. So again, if you remember, one reason we care about such categories is because they give us a knot and link invariants. And well, here's explicitly how they do. Here's a formula which tells me how to interpret this crossing as some morphism in this category. All right. Maybe I should say a little bit about how this correspondence goes. Well, my single self-dual object just corresponds to the standard representation of SL2. And then I just need to tell you where, I guess, these morphisms go. And these are just the maps from, say, that thing tensor itself onto the antisymmetric tensors, and then the inclusion of the antisymmetric tensors in that thing tensor itself. Okay, from there you can maybe go home and try to prove this theorem, but I'll indicate a sketch of how it goes a bit later. Okay. So here's some nice applications of this structure. So as I mentioned earlier, or maybe I'm currently mentioning still, we get link invariants. And what this essentially recovers is what's known as the Kaufman bracket description of the Jones polynomial. And one, I think, important thing to observe if you're maybe not quite familiar with the history of applications of the Jones polynomial in knot theory is really the first big thing that the Jones polynomial took down, first classical conjecture, big classical conjecture, was known as the Tate Conjecture. And that was made accessible somehow after this diagrammatic interpretation of the Jones polynomial was introduced. So the diagrammatics really does something for you. It really provides a useful tool that was useful in proving a big unsolved result. But if you recall bullet point 2 up above, I said that I really view this these diagrammatic descriptions as a foundation for categorification, and somehow I really mean that literally. So there's a description of Kavanagh homology, Kavanagh's categorification of the Jones polynomial, in terms of what's maybe now called the Barnaton 2 category. And you can essentially reinvent Barnaton by taking this relation and trying to interpret it as an isomorphism, circle isomorphic to Q plus Q inverse. And if you think about what that should mean in a category, that's somehow saying that the circle should be isomorphic to 2 copies of some other thing. You could try to write down what that would mean. Maybe you'd expect for morphisms between things like circles to be surfaces. And if you just try to write down what it would mean for the circle to be isomorphic to 2 copies of, say, the empty thing, you'll maybe naturally be led to consider things that look like caps and sort of cap and cup surfaces. And essentially what these relations I've written down here are relations which prescribe sort of a 2x1 and 1x2 matrix realizing this isomorphism. And when I say foundation, somehow you can see that the foundation is right here. You take these diagrammatics and you really build on top of that foundation in a perpendicular direction some other diagrammatics, which leads to the categorified stuff. So this is an application that I want to keep in mind as we discuss some of these other categories. Okay. So that's essentially the SL2 case, and maybe very quickly. What's next in our list? Well, you start enumerating simple complex Lie algebras. You enumerate them by rank. You say the next three simplest complex Lie algebras are the rank 2 ones, SL3, SP4, also known as SO5, and G2. And in this setting, Kuperberg proves an analogous result. So here's maybe some quick way to summarize 3 of Kuperberg's theorems into just one. And the statement is, take your rank 2 complex Lie algebra. Then this category of fundamental representations is equivalent to, again, the category is pivotal, which means you'll see some caps and cups sort of implicit in this description, and wiggling around in the plane, this planar isotopy, also implicit. Category generated by, I claim, 2 objects. And then you should read the bit that's a little lighter. In the case that you're not SL3, these objects are self-dual. In the case that we are SL3, these objects are dual to each other. And then in this case, we actually need some generating morphisms. Before, somehow all the generating morphisms were implied just by the object and being pivotal. But for here, we need some morphisms. And in each case, there are less than or equal to 2 trivalent vertices. And in each case, for each of these 3 simple complex Lie algebras, there are less than or equal to 8 local relations. So let me make this precise for, well, not SL3, that's maybe the predictable choice. I'll make this precise for SP4. So here's, in this case, there's just one generator. So I guess I promised less than or equal to 2. There it is. Again, there'll be some implied by this word pivotal, which means you need caps and cups, and you need straight lines labeled 1 and 2. You can see that I'm starting to shift to a color-coded version of keeping track of the labels of the strings in my monoidal category. So the objects are 1 and 2. 1 is black, 2 is blue. And this is all somehow after this generator implicit as to what the domains and codomains of these morphisms are. So there's the generator. Again, I can stack these things side by side, top to bottom. I have caps and cups. So a lot of things you can build. You can basically build any trivalent graph locally modeled by this picture. And then we need some relations. And I guess I promised fewer than 8. In this case, there's 1, 2, 3, 1, 2, 3, 4, 5, 6. Okay, so I think for 8, for G2, you need 8 relations. Okay. And so these graphs, these trivalent graphs that are built out of our generating pieces are called webs. Somehow they kind of look like spider webs. Okay, so again, very efficient presentation of this category. I can fit it on one iPad screen turned sideways. Again, an explicit formula for the braiding. So now I've just defined the crossing, which is, I suppose, 1 labeled. I could write down the one that's 2 labeled, although you can actually somehow deduce it from this one. Again, this gives you some very explicit formulation of a certain knot and link invariant. Essentially, take your knot diagram, apply this relation, get some linear combination of these webs, use these relations to simplify. Of course, you need some theorem which tells you can simplify, but that's sort of hardwired into this theorem of Kuperberg. And again, just one nice application is these again form some foundation for a link homology theory. So in this case, this is, oh, well, I guess I'm writing down the SL3 case. Shift from this rank 2 Lie algebra to a slightly better understood one, SL3. you'll see similar pictures, similar relations, and what you find is that this web formulation of the category of quantum SL3 representations, so for SL3, this forms, again, a foundation, see down here at the bottom, for Kovanov's SL3 foam 2 category, which again is some higher categorical structure mimicking, or sort of, maybe I should say, in the vein of this Barnaton 2 category, from which you can compute SL3 link homology. So I think that's been 25 minutes. Is this a good place to pause? Okay. So I guess 5-minute breather. Are questions allowed during the breather, or?
Oh
okay.
yeah, go for it.
Okay, so happy to answer questions. I'm also happy just to sip my tea. So people don't feel obliged. Maybe I can stop the share. Yeah, go for it.
Do you have foams for supergroups? You know, like GL11 something.
Yeah. So we want foams for supergroups. I think current state of the art is foams for SLN. Some version of Homfley foams, but that's secretly just some alternative description of 2 category of singular Bott-Samuelson bimodules in type A. There's some way to recover something like foams for, I guess, GL0N from that, but it's really just doing something with the Homfley foams and applying some specialization. And beyond that, I think the foam world is wide open. It's actually maybe the main reason I'm interested in this problem for webs outside type A is I want foams outside type A because I want to be able to give topological applications for link homologies outside type A. Who knows what sort of interesting information is lurking there. And maybe my slightly biased viewpoint is that the best way to cook up applications of link homologies is to have these hands-on foam descriptions which are amenable to topological arguments. I could say more about that if people are curious. But no, to answer the original question, no, I would love to tell you what a GL11 foam is. Maybe I'm hoping to in some number of years.
Are there webs for supergroups too?
So webs for supergroups. Yes. So let's see. I'm almost certainly going to leave off some names. So I think this appears in work of Jonathan Grant. Also, I think in work of Tugendhauer, Vaz, Wedrich. Also related work of Queflex, Sartori. Almost certainly I've forgot a paper. And maybe also some recent work of Robert Wagner. I know they have this statesum paper for GLMN link invariants. Presumably there's some webs there too. So yeah, the foundations I think in type A are there, but figuring out what the foams should be it's an interesting open problem I think at the moment.
Elijah asks in chat if you can define link homology without foams.
Certainly. So you can, I mean, Kovanov's original definition did not use foams. Let's see, the matrix factorizations don't use foams. The Kautas-Chemnitzer approach doesn't use foams. So certainly there are other descriptions. I guess where I think the utility of foams comes in is most of the topological applications of link homology involve things like Rasmussen's S invariant or its generalizations. Those things come from deformations of link homology theories. And from my perspective, deformations of link homology theories come from deformations of foam categories. And so if you want to cook up fun things to do, or fun topological applications of your link homologies, my roadmap for that is find the foams, deform the foams, and use the deformed invariants to cook up interesting concordance invariants and slice genus bounds. So maybe that's what's lurking in the back of this whole program, at least from some perspective. Sorry,
I think it's a good time to resume now.
Great. Just so no one is, I think I left off the category O approach to link homologies via Sussin and Stropel, Mazurchuk Stropel. That also does not use foams, just so I'm ticking every, and neither does Ben Webster's approach. Don't want to leave anyone off the list. So yes, there are lots of link homology constructions that don't use foams. I may be just partial to the foam construction.
Did he freeze for anyone else, or is that just me?
Yeah, we can. I think it's probably a good time to resume the talk, everyone.
He's frozen, I think.
Oh, really?
It's frozen for me as well. Oh, yeah.
Oh, no. Well, I afraid my... I hadn't realized what was going on, actually, for a couple of minutes there.
Who wants to give his talk?
Yeah. Can we extend the recording after the 1 hour to make up for lost time?
Yeah, that's easily done.
Okay, that's good. So we're cool on that front.
Yeah.
I guess we can still wait for a few more minutes then.
While we're waiting, so can anybody tell me that in the SP4 case, and there are two generators, 1 and 2. So which two representations are those two?
The fundamental representations, the 4- and 5-dimensional ones. So because one of those is not tilting in characteristic 2, then you can kind of expect that there's going to be some quantum 2s in the denominator in that presentation.
Thanks, Ben.
So all those other link homologies you constructed, or most of them, have some algebraic structure in the background, like Zirkel bimodules or some like Kovanov's this 2-dimensional vector space V, which is roughly the same thing. And you can deform algebraically those things as well. So good, there he is.
Okay, sorry. Maybe I should have warned people. There are 2 academics in this house, and sometimes we overly tax our I don't know, our Wi-Fi, our Zoom. So I guess it was a good time as any for something to cut out. So slightly extended break. Hopefully we're good from here on. Great. Okay, I see people's video, so that tells me that everyone can hear me. Okay, so jumping right back in. So maybe one thing to pause and think about before moving on is how are these results proved? How do you prove that this category of SL2 representations is this category of planar curves? How do you prove that these, in the rank 2 case, these categories of webs? And so here's just a very quick rundown on my view of how these things get proved. So step 1 is you use some sort of representation theoretic duality to essentially show that you have a full, essentially surjective functor. So that says that you surject onto the objects that you want, and you surject onto morphisms from what you call a free web category. So just the thing with the generators before I impose any relations. And this really just relies on the fact that these categories are braided monoidal, and the fact that you can use these sort of dualities to show that the braid group surjects onto certain Hom spaces. I view this as somehow this is a straightforward part of this. I mean, you have to figure out what the right generators are, but it's usually pretty easy to deduce what they need to be, and show that you can build the braiding out of those things. And so then you just hit this thing over the head with some results that say, we know certain groups or certain algebras surject onto certain Hom spaces. That gets the ball rolling. So then you want to find the relations. That leads you to step 2, where, well, you just look at some Hom spaces for small numbers of tensor products of generators. Just take a few generators, tensor product them together, maybe 1 or 2, and just count dimensions, and then see how many graphs, how many webs you can build out of your generators. And that will in some cases tell you that you need to impose some number of relations between those graphs. And then what you do is you say, well, if this theorem is going to be true, my diagrammatic category better be braided monoidal, better in fact be a ribbon category. And you can use those restrictions to actually really churn some big crank that will eventually tell you, what the coefficients in those relations need to be. So if you're curious, you could look in my paper with Tatum. We actually just do steps 1 and 2 in this type C3 case, the SP6 case. This is roughly how some of the previous proofs had gone, and this is explicitly how we get our guess for what should happen in higher rank. But then you run into step 3, and step 3 is the hard step. You need to show that your relations allow your webs to be simplified into some sort of special class of webs. And special class sort of depends on which setting you're in. But you want to be able to take things and simplify them with your relations as much as possible. And then what you then would like to assert is that things which cannot be simplified further, that's your candidate for some of the basis for your morphism spaces. And then you do the really hard work, which is you somehow produce some bijection between that basis and some known basis, or at least show that basis has the same size as Hom spaces. And so I claim that this is actually hard in 2 ways. It's hard in some sort of graph theoretic combinatorial way of just what does it mean to simplify? How can you simplify? Why can you always simplify? Why can you always end up in a good place once you've simplified? And then it's hard another way is once you've even proved all that, you need to then count all the simplest, the sort of unsimplifiable things, count them and show that you have the right number of them. So step 3 is really where things get dicey. Okay. So going back to our list of Lie algebras, you might think the next thing to consider would be just the rank 3 ones. We've done rank 1 and 2. But you, might try the first rank 3 one that you think will be the simplest, SL4, and try this procedure. And I claim that you run into a problem right away. And so this was maybe some attempts at this SL4 were done in work of Dong-Sok Kim, also in work of Scott Morrison. And somehow one problem that you run into is, when you looked at this list of relations earlier, it was sort of obvious that, some collection of these relations look like they're simplifying some measure of complexity on the graph. They allow you to pluck out somehow unigons, digons, triangles, and you can even prove that this set of relations allows you to remove things like any square faces of the corresponding graph. And so these relations allow you to simplify somehow like face complexity. And that's how this argument that takes you from arbitrary graphs you might build to your simplest class of graphs goes. So again, these simplified ones are ones with certain types of faces. But for SL4, you're led right to a relation of this form. And now it's really not clear which side of this relation is the simpler one. They actually look pretty similar. So I claim that maybe the first way in which step 3 is hard immediately becomes hard when you look at SL4, and actually when you look at any of the rank 3 Lie algebras. So what's the solution? Well, you abandon steps 1, 2, and 3, and you do some fancy work. So this is work of Cottis, Kamnitzer, Morrison that builds off some earlier work of Cottis, Kamnitzer, Licata, and also builds off of Scott Morrison's thesis. And they say, well, we should revisit this problem from the perspective of a really useful representation theoretic duality called Skew duality. What this duality says is consider this space. So take C to the k tensor C to the n. Take a big wedge product, so take the exterior algebra of that thing. This admits actions of GLK and GLN, and there's a quantum analog of this. And if you stare at this, you notice that somehow because the GLK and the GLN are acting on somehow different pieces of this tensor product, the actions commute. And what you juice out of this, and this paper is a beautiful read, one of my favorite papers of the past decade for sure. What you juice out of this is some functor that maps from some version of quantum GLK, viewed as a category, to this category that you're interested in, this category of fundamental SLN representations. And what this allows you to do is sort of a completely different way of constructing relations. Because I have this functor, relations here must get taken to relations here. And what they show is that somehow there's some basic defining relations in quantum, well, I've written GLK, but just imagine quantum SLK if you don't thinking about GL. I mean, one of those basic relations that you learn in, learn about SL2 is you have this EF minus FE equals H relation. And that relation exactly gets transported to, maybe I should doctor this one a little better, some relation between graphs, which says that minus that equals this. So somehow I see this E here is like this bit of the web tilted that way. This F here is that one tilted that way. You notice over here I just see them tilted in the opposite order. So I see something which looks like EF, minus something which looks like FE, and then I see something which looks like, well, maybe the weight that we're living in, which is determined by the K and the L down here. Okay, so I could give maybe an hour-and-a-half lecture on Skew duality on its own, but this is some indication of how this procedure works. It's some nice fancy duality, which then not only gives you a way to sort of immediately get a list of relations that need to be imposed on the right-hand side, but also provides a means to show you found them all. And that is essentially because we understand the representation theory of quantum SLK, quantum GLK pretty well. And maybe how long ago told us how to understand this duality pretty well. So you bring in some other tools, fancier representation theoretic tools, and they give a completely different approach to this problem. So we've covered rank 1, we've covered rank 2. We've seen that maybe the methods for solving this problem in ranks 1 and 2 don't immediately give us the answer in rank 3. But for SLN, you can try some different idea, and that actually gives you everything. Of course, then you have an idea, and this appeared in a work of Sartori Tubenhauer, well, Skew duality worked pretty well in type A. If we look at Howe's old paper, he tells me lots of other types of how dualities, both skew and symmetric versions. Maybe we should try those and see what they give us. So in a very interesting paper by Sartori Tubenhauer, they try to push this idea, saying, let's look at how dualities and other types, and let's turn this Kamnitzer-Morrison machine on, and let's solve this problem. But unfortunately, what they end up showing, and I think this is sort of the interesting takeaway of their paper, is that outside of type A, how dualities don't quantize like you want them to. So how was working with dualities between simple Lie algebras. Part of the work in Kamnitzer-Morrison was doing it for the quantum groups. And it turns out that when you quantize in types, quantize how dualities in types B, C, D, one of these things ends up staying a quantum group, but the other one becomes some relative of the quantum group, which is not the relative that you're looking for. So a takeaway, or my takeaway from this beautiful Sartori Tubenhauer paper is this procedure will not just allow you to turn on the Kamnitzer-Morrison machine, because when you quantize something that you want to remain a quantum group becomes a different algebra that is no longer immediately relevant to this problem. Okay. So what do? Well, you don't give up. You try another approach. So one observation that you can make is that, well, if you stare at what how duality gives you in type A, it actually gives you several implications for webs that, of course, come from how duality. But once you observe those facts, you realize that they can actually be exploited without ever using the concept of how duality whatsoever. So I want to go through this list because, well, this is the list which served as a motivation for the type C work, which I'll be talking about in a second. So the first thing that Kamnitzer-Morrison tell us is that, well, in the process of using how duality to describe webs, they were led to consider webs that were in ladder form. So these are trivalent graphs as before, but we require a bit more rigidity. We require them to all consist of these edges which are sort of the uprights of a ladder, and then also these edges which would be essentially the things that you step on while you're climbing the ladder, these ladder rungs. And so what naturally comes out of their description, their sort of diagrammatic description of skew how duality, are these ladder rungs, webs in ladder form, where essentially I translate between, the ladder form and the object, sorry, the element in the dual quantum group, by looking at where the rung is placed and whether it's slanted sort of up into the left or up into the right. So the prescription is somehow, I see here, the first thing I read is an E2. That's because the top, a bit of this that's interesting, the top rung is pointing, or sort of slanted up into the left, and is between, sort of is in the second slot in which it could appear. And then here I see an F1, that's over here, the first slot, slanted the other way. And then here I see an E3, that's in the third slot, again, slanted the up to the left way. Okay, so this sort of falls out of their description of skew how duality, and they show that all webs, all SLN webs can be placed in this form. The next observation is that, well, I know the PBW theorem on the dual side. PBW theorem allows me to say take expressions in the quantum group, which are say sequences of E's, F's, and I guess classically it would be something like H's, in the quantum setting things like K's, and rearrange to put all of my E's on one side and all of my F's on the other. And that immediately implies a PBW-like theorem for rungs in these ladders. And so here I've just written down some further relations in this SLN web category. And you note that each one of these relations allows me to take an up left slanted rung appearing above an up right slanted rung and put them in the opposite order. So I pull the E rung below the F rung as I go from left to right in all of these equations. And somehow in the last one that happens, but like up to lower order terms where I have fewer rungs. So this is another thing. And again, this follows from knowing skew-how duality, but I can state this fact without saying anything about how duality. And then maybe a third takeaway, which probably I won't have the time to get to, is that it also suggests that, well, when I stated how duality, I didn't say SL, I said GL when talking about the dualities, and then somehow SL appeared here. And so another takeaway is that how duality is really about GLN, GLK, but we'll see if we get to that takeaway. Okay, so what do these takeaways now tell me? Well, I claim that just knowing 1 and 2, that I can put things in ladder form and that I can do this ladder PDW stuff, using just those facts, you can prove that all closed webs, those without any boundary points, essentially the endomorphisms of the monodal unit, can be evaluated down to scalars. You can also use this to prove that all Hom spaces in this category, again, that you define by certain trivalent graphs, modulo certain relations, are finite dimensional. Note that a priori that's far from the case, right? If you generally try to define things by generators and relations and say, look at the set of things I can build out of these pieces, there's probably an infinite number of things, and then impose these relations, and look at all linear combinations of such things, modulo those relations, you're typically not going to get something which is finite dimensional. You're probably going to get something which is horribly infinite dimensional. So even knowing that these Hom spaces are finite dimensional is something I claim that is hard a priori, but knowing that you can put things in ladder form and knowing that you have rung PDW, you can show that Hom spaces are finite dimensional. And lastly, you can show that the trace of this category, which is some categorical operation you can apply, which is like a version of decategorification that's maybe more amenable to diagrammatically defined things, agrees with what it should. So I have a trace in this setting also, because the category of quantum group representations is semi-simple. I know the trace is going to agree with the Grothendieck group. And so I can prove a lot of things, a lot of properties that I would expect this web category to have, knowing only 1 and 2. And of course, they somehow also set the stage for finishing off the proof by giving you some means to get like the simplest things that you then want to count and show have the right dimension. Okay, so that's maybe the some additional takeaways besides the takeaway that skew-how duality is useful. This is the takeaway that, well, even if we don't have skew-how duality, some consequences of skew-how duality might be useful. I think I'm officially supposed to end right now. Is it okay if I take the 5 minutes due to the...
You can take a little bit more, yeah.
Okay, great. It'd be good if I can actually talk about the new stuff. So, some new stuff. So let me define a category for you. I will call it Web SP6. As before, it's a C-adjoint Q linear pivotal category. It's freely generated by now, well, when rank 3 self-dual objects in this case. And I need 2 generating morphisms right here. Somehow this is like 1, 1 goes to 2 and 1, 2 goes to 3. And then modulo some list of relations. So it's a little longer than before. I think you'll expect the number of relations to grow as the number of generators grows, but still something that can fit on one screen. So here it is. This category was exactly invented just by following steps 1 and 2 that I outlined earlier. So use some dualities to get some guesses of generating morphisms. you prove that you will essentially surject onto the category of representations using something like Scherval duality. Now it's called Brouwer-Scherval duality. You get the coefficients here by insisting that this category is braided monoidal, and further that it's ribbon. You maybe use some facts, something like the dimensions of certain representations. That basically gives you this category and tells you that it has to be this one, modulo, well, there's actually some flexibility in your choice of that number and that number, which then propagates to other coefficients. That's the only flexibility. And then of course, you might not know that you have all of the relations, but at the moment we think we have them all. Because in joint work with Logan Tatum, just now I can say former UNC graduate student, we proved some theorems. We showed that this category is ribbon. So that's braided monoidal plus some nice additional properties that tell you get invariants of framed knots and links. We show that there's a full, essentially surjective braided monoidal functor. Probably I should say pivotal somewhere in there also, from this web category to the category of fundamental representations. We then show, using, again, these takeaways of Howe duality, this idea of you should try to put things in ladder form and you should try to prove a Rung PBW theorem. So we do those things, and we show that the endomorphism of the monoidal unit is what you think it is, a one-dimensional vector space generated by the empty diagram. That means that you can evaluate all closed webs. And moreover, we're able to show that all Hom spaces here are finite dimensional, or of course, a priori, look at all graphs you can build out of these pieces, look at the vector space spanned by all such things, and impose these relations. Trying to prove that's a finite dimensional vector space just by hand is quite hard. This Rung PBW theorem ends up giving it to you. We also prove this analogous decategorification result, which basically tells you that in some sense, if we knew our category was semi-simple, we would know that it's the right category. But somehow proving that diagrammatically defined categories are semi-simple takes some work. Great. And of course, we conjecture that this functor is faithful. That's the one thing left in showing that these are actually, the same equivalent categories. We conjecture this is faithful. And I should say that resolution of this is in progress with this cast of characters. Maybe this is a shameless time to get the organizer of the conference's name on the board, but also some good press because Elijah is a grad student, Logan is a recent grad student. They're both top-notch mathematicians, so let's get their names out there, or I'm gonna get their names out there. I have the floor. Great. Since I'm running out of time, let me just conclude with some remarks. So as I mentioned, theorem 1 follows via the easy steps. I mentioned before, easy's in quotes, because of course there's still some hard work to do there, but it's not nearly as complicated as sort of the more involved things, showing that your Hom spaces are sort of are not too big. And again, these theorems 2 and 3, they follow by this Rung PBW idea. And we actually apply it not to this category, but to a related category of GSP6 ladder webs. So again, we took inspiration from the fact that in type A, Howe duality is really a GL thing, not an SL thing. And I think for a day, we thought we invented something new, GSP. And then of course we did a Google search and realized that some people have been thinking about the Lie group GSP for years. Maybe I'm revealing my origins in topology, and somehow in my algebra education, I never learned about GSP. Anyways, this is motivated by, again, this observation 3 about ladders in type A, and yeah, you can read about this group online, as it turns out. And maybe another takeaway, and maybe this will be the last takeaway, is that what this tells us, what these theorems tell us, is that Well, because I can evaluate any closed web to a scalar, right? That was the takeaway of, or that was maybe the statement, first statement of theorem 2. And because we've shown that this category is ribbon, in particular that means we give a formula for the braiding, this gives a Kaufman-esque formulation of the quantum SP6 link invariant, meaning take your link diagram, apply this relation everywhere, and then our theorem tells you that that linear combination of webs that it spits out can be evaluated down to scalars, and that scalar will be, because of theorem 1, the quantum SP6 link invariant. So somehow the informal takeaway is that if you're interested in topological applications, this category somehow is good enough. So for example, I think good enough to start playing around with and thinking about, maybe if you want explicit descriptions of associated TQFT, this is maybe some place to start. If you want to start thinking about link homology, is also a place to start. Great. That said, I don't know, I think we're fairly confident that this is the right category and that it will be shown to be the right category, hopefully in the near future. And with that, I think there's not even anything else. I did it. So I'll wrap up here. Thanks for your time.
Thank you very much, David. Any questions? I'm a bit curious as to what do you think it would take to go to SP2N? I mean, obviously the relations would be much more complicated, but is there like an intrinsic difficulty?
So yeah, is there intrinsic difficulty? I mean, there really shouldn't be. And so I didn't describe the technique that we're aiming to use to prove that these Helm spaces are small enough. And this is in a beautiful paper of Ben's called Light Ladders and Clasp Conjectures. And Ben basically gives a alternative proof that SLN webs in type A are the right category. Essentially by showing you how to build web bases. And so in theory, we could sort of run the steps 1 and 2 crank here to produce the relations. Actually, in Logan's thesis, there's some maybe conjectured SP2N relations. It's not a claim that they're all of them, but it's a list of ones which we know need to be imposed. So maybe pushing that stuff a little harder will give you a good guess of what relations you want. And then the idea is that this light ladder technology of Ben's will then allow you to prove that your Helm spaces are small enough. Somehow the philosophy, again, is you just want to make sure you impose enough relations so that you can run this rung PBW stuff. Once you know that, the proofs from our paper, which focuses on rank 3, should just churn. And the hope is that once we've written this follow-up, that machinery might just churn as well. Maybe it might even be in the follow-up. I don't know. We'll see how fast it goes.
So there's also a question in the chat asking about B and ND, and I suppose the same answer could in principle be given for B and ND.
I think the same answer should work. So to be honest, I've forgotten. It's been so long since we started focusing on type C that I forgot why we went down that road. So originally, Logan and I started thinking about this maybe 3 years ago when he was a younger UNC grad student. And originally the idea was to start with, I mean, Kuperberg has this nice description of B2 and C2. And so, you want to build off of, or we wanted to build off of stuff that was known. So it seemed natural to try either type B or type C. And when we started just actually playing around with things, type C seemed to be the one which was just a little nicer. But in principle, one could revisit that, and maybe even revisiting it from a couple of years down the road would see that it wasn't actually as scary as we thought it was. So yeah, in principle, I don't see any obstruction to those types. And I mean, the question is maybe even, what about exceptional algebras? Again, the procedure is it ends up being quite general. We were just focusing on type C for convenience.
Right. The light ladder philosophy should apply to any monoidal category that's generically semi-simple. But to figure out what to actually do, you need to have a pretty good understanding of the fundamental representations and their weights and how the plethysm works combinatorially. And that's kind of a pain in other types outside of A, B, C, D, maybe.
Yeah. I guess I haven't looked into what E8 plethism looks like.
We have a couple more questions in the chat, so maybe it would be a better idea to ask the questions if we can, so everyone can hear them.
Yeah, fire away.
Sure. So I have a quick question. So my question is, once these web categories are constructed, do we expect any major barriers to constructing the appropriate foam categories, or do we expect those to follow more or less pretty rapidly?
I think it's there's a lot to do. So you see that denominators start showing up in these relations. So dealing with denominators is typically pretty hard categorically. It suggests you need to look at semi-infinite complexes, which would mean that in contrast to, say, the type A stuff, so in the type A stuff, you can categorify the web categories additively, and you only need to pass to complexes once you start thinking about link invariants. But those denominators, if you sort of can't scale them all away, which again, there's some flexibility in your normalization of this category. So maybe some good rescaling.
It's impossible to rescale them away.
Yeah, I mean, you can always multiply and clear denominators, and maybe that's the foam relation, or that's the relation you want to categorify. I mean, there's infinite things to try. But yeah, of course, the denominators suggest that you should have some difficulties, and yeah, it's quite complicated then when you sort of the very first step are dealing not with additive categories but with triangulated categories. So no, it's an interesting problem. I should say I actually have a very enterprising undergrad starting to think about this just for type C2, and so there might be something to report back on. I don't know. Is there Quacks 2 next year, Ben?
There will be another conference organized by our FRT, but won't be called Quacks.
It's not going to be D2. See if anyone grew up in the 90s and gets the reference.
I was there.
Yeah, so it is not straightforward. I mean, foams, even in type A, there's a long history starting with Kovanov's work in SL3, Makai-Stoshik-Vaz in SLN, me and OL have some papers on this, and people are still thinking about this, interesting recent work of Robert Wagner. So yeah, foams are hard. Somehow it's nice to be able to stare at a plane and simplify things there. We start thinking about simplifying things, complicated objects in three-dimensional space. Things get much trickier. If you think it's tough proving you can evaluate a web, try proving you can evaluate a foam.
One more thing to add to that, which is that in type A, foams are really just singular Zirkel bimodules. And that's because you have Sure-Weil duality, which says that it's actually secretly the Heck algebra that's acting on these tensor products. But outside of type A, it's not singular Zirkel bimodules. The singular Zirkel bimodules are hard enough, but there's something even more.
Yeah, that then raises a good point. And in fact, one other reason why, if you don't even care about link homologies at all, you might be interested in these foam categories is the thing which is Sure-Weil dual in types BCD is known as a BMW algebra. And you might just, because you're an algebraist, be interested in categorifying that thing. And so you might try to do this in a very roundabout way. You observe that if you had started off thinking about foams and push that theory far enough, you would eventually arrive at this GL infinity foam category, and then observe that gives you the category of or category of singular about Samuelson bimodules, and so produces for you a categorification of the Heck algebroid. So you might try to run that story in types BCD and use the phones to somehow tell you what the categorification of the BMW algebra should be, and then maybe even from that try to guess what the appropriate category of bimodules is. And I think there's all sorts of fun stuff to do here. Yeah, maybe, hopefully, some people in the audience will join in the fun.
All right, do we have any other questions? If not,
I have a
thank you
very
very much,
stupid
David.
question.
Oh,
Sorry.
question.
Yes, so type D, it's
What?
simply list. Does it help at all? Like, there are lots of geometric constructions of representations in type D, like using quivarieties and other things, but like, does it help at all? I know nothing like about webs and type D or whatever, but
I also know
abstractly,
nothing.
like, would you expect that being simply list is slightly easier, or there is no advantage?
I mean, from my perspective, it didn't seem that type D was simpler, but I definitely don't come to this stuff from the perspective of geometric representation theory. So I maybe not completely qualified to to weigh in on whether being simply laced and having nice sort of geometric representation theoretic structures surrounding me would help with webs. From our work on this, it simply laced or not didn't seem to play a role.
I think it will end up simplifying the form of the light ladders, like reducing rung thicknesses, if that makes a difference. I also think it'll reduce the complexity of clasp formulas, which are also important. Like the coefficients in Jones-Wendell projectors are going to be easier to understand. But aside from that, I don't think it makes a big difference.
All right, everyone. Thank you very much, David. So we'll see you back tomorrow.
Thanks for all.